Welcome to my poster. I'm Prasanta Kumar Ghosh from University of Southern California, and my advisor is Professor Shrikant Narayanan. Here today I'm going to present a result which demonstrates an information theoretic account of the production perception link in human speech communication. So when one subject speaks to another subject, the talker uses his speech production organs like tongues, jaw, lips, and on the other side, the listener uses his ear to listen to the sound. Now, in the ear of the listener, there is a snail-like structure called cochlea, which works as a filter bank. And if you look at that cochlea, the cochlear frequency axis is not really uniform, in the sense that if you consider uniform filter bank on the cochlear axis, let's say this is the cochlear axis, then that corresponds to non-uniform filters in the standard frequency axis. So, and this relationship is mostly logarithmic. So what we are asking the question here is that why exactly we have this specific logarithmic frequency scale in the auditory filters, and is there any reason from the speech communication perspective? And the way we are answering the question is by assuming that the listener is going to decode what was transmitted by the talker. That means the code that was transmitted by the talker should have the least uncertainty given the output of the filter banks, right? So the code that you're using in the transmitter side, that's the talker side, is the articulatory representation. That means how the tongue or the jaw and the lips moved in the mid-sagittal plane, and we got that using electromagnetic articulography technology. And the same rate, what we are doing, we are computing the output of this filter bank, any arbitrary filter bank, not necessarily this particular filter bank, using the output energy of all the filters in the filter bank. Let's say we call the filter bank as BL, and the output is the log energy of each of the filters. So we have a L-dimensional representation. Now the question you're asking is, what is the best filter bank that will provide us the least uncertainty about the articulatory representation? And that we can easily figure out by maximizing the mutual information between the XBL and Y. And we cannot have a closed form solution of the mutual information, so we use an estimate of the mutual information. And we solve this by a greedy approach, where we start with a all-pass filter, and then in each level, we divide each filter in the previous level into two sub-filters, and choose the one which gives the maximum mutual information between XBL and Y. And we proceed that way, go up to L equal to 20 filters, and this is how we got the optimized filter banks, which are not exactly same as the empirically established auditory filter bank, which is shown here also. But what is interesting is that there is a similarity in the warping function between the red curve, that is the auditory filter bank, and the optimized filter bank. And when we run all this optimization for 45 different subjects, 40 English, 3 Cantonese, and 2 Georgian, we see that the warping functions are on average similar to the auditory filter bank warping function. And in general, the mutual information obtained by the auditory filter bank is more than 90% than what best can be achieved. So this indicates that the auditory filter bank is not a random choice. Rather, if you choose this auditory filter bank, we'll have the minimum uncertainty about the transmitted code, which is represented using this articulatory representation. So this provides us a reason as to why the auditory filter bank will have specifically this kind of logarithmic scale in its frequency axis. So thank you for your attention. If you have any question, comments, you can send me an email. Thank you.